Okay. Yeah, so let me thank the organizers for putting all of this together. So yeah, I'll try to give hopefully a sort of friendly introduction to some recent work that's really began about 7 years ago in discovering sort of viscous flows of electrons in sort of pure solid state devices. So let me begin by just sort of reviewing, what solid state physics is in a 3-minute nutshell. So let's say here we have, this is my sketch of a metal, okay, and there's a lot of junk inside of metals. So first you could maybe think there's an ionic lattice. Okay, so here I have my ions, right? They're all bonded together. These ions are, of course, not static. At finite temperature, they're vibrating a little bit. And the vibrations of these ions are called phonons. In a metal, there will be some electrons that are unbound, right, to individual atoms that are just free to move around. So those all put these little solid dots. Okay, so here I have electrons, and these can move around through the whole system. And then additionally, I can, no crystal is perfect. So there will always be some kinds of defects and impurities. So let's just say here, I have an impurity atom. It may be, for example, that the wrong kind of atom is in the lattice, okay? And, real solids have many degrees of freedom. There will be many impurities and many phonons and electrons. And, generally we expect this solid to thermalize, right? So we don't just have a gas of non-interacting electrons and non-interacting phonons. Okay, so we expect that this system will eventually reach thermal equilibrium. And if we ask what are the dynamics of how this system ought to reach thermal equilibrium, well, that's where maybe we might invoke this theory called hydrodynamics to attempt to explain the process of thermalization in solids. Okay, now depending on what you define hydrodynamics to be, and I would say that although there should be one definition in the community, I find that there's not. So depending on your definition, the answer to this question can either always be yes or sometimes rarely be yes, sort of. And in the first part of the talk, I'll sort of clarify what exactly I mean by that. Yeah, before I do that, let me just maybe sort of boring review for this audience, but let me just very quickly summarize what it means from my perspective to sort of be in a hydrodynamic limit. So why would I even invoke this claim that electrons might behave like a fluid, just from stating that they thermalize? Well, if we take, again, let's draw our same cartoon metal again, okay? Let's say that I define what I'll call a mean free path with little l, okay? And I'm just going to postulate that there exists some length scale, little l. On length scales larger than this, the system, will locally tend to approach equilibrium pretty quickly. And on length scales short compared to this, I need sort of full microscopic data about the underlying system to describe the dynamics. Okay. You can roughly think this is the distance between particle collisions, but one can make sense of a mean free path even if particles are not well defined. You just have some soup of matter. Okay. All right. So now, I can think that my metal consists of little blobs, each one maybe of size this mean free path. And, essentially by assumption, each blob in this metal will attempt to thermalize. And after, let's say, a mean free time tau, okay, each one of these little blobs is in thermal equilibrium. Okay, so thermal equilibrium for this metal, I might characterize by a couple parameters. So I might characterize equilibrium by some temperature T. I may also care about the number of electrons. So let's say the number density of electrons, which I'll call rho. Temperature T is associated with, is sort of the dual in thermodynamics to energy conservation. So I could also equivalently think of energy density epsilon if I wanted here. And then we might also throw in here the momentum density of the system, which I'll denote with little pi, and then a vector index because momentum is a vector. We'll come back to this assumption a little bit later, okay? But let's run with it for the moment, okay? So each one of these blobs is reaching thermal equilibrium locally. And so I can characterize each blob essentially just by these thermodynamic parameters. And my assertion will be that I need nothing else to characterize each blob, okay? Roughly speaking, any other degree of freedom in the system will tend to relax to 0 effectively. And it will do so on this timescale tau, because if it didn't, if there was some slower degree of freedom, then I should have redefined the mean free time to be associated with the slower decay rate, okay? So on the longest timescales, only these conserved quantities will have slow dynamics, okay? Okay, and so hydrodynamics, from my perspective, will be the theory that describes the slow dynamics of these conserved quantities in late time. Okay, the way hydrodynamics is set up, right, is that we say if, maybe this sort of section of my metal is of size capital L, okay, then if this capital L is very large compared to my mean free path, then hydro should be a reasonable approximation. And what hydro will correspond to is an equation of motion for these three conserved quantities. So for example, for charge, I'll write down a equation that looks like this. So the fact that dt rho is a total divergence just tells me rho is conserved. Okay. And the fact that this is, and the fact that ji will be expressed as a local function tells me that matter doesn't teleport. Okay. Similarly, I can write down an equation for my momentum. And we're going to ignore energy. For the purposes of today's talk, there's really nothing interesting I can say that depends on energy conservation, so we'll just ignore it. Okay. All right. And so hydrodynamics will correspond both to asserting these equations of motion and also telling you expressions for J and tau. All right. Now, in textbook fluid dynamics, we assume something special to write down formulas for J and tau. So a textbook fluid has a symmetry that I'll call Galilean invariants. So, fluids like air and water, we can think of them as being compatible with Galileo's principle of relativity. So if you go to a reference frame moving at some velocity v, the physics looks the same as long as that velocity is constant. And this turns out to be strongly constraining on the form of J and tau. So one finds in particular that the current J must be proportional to the momentum density pi. This turns out to be an exact statement. The constant prefactor, I'll call m. This is just the mass of my particles. The stress tensor also turns out to be quite constrained. So this one, so there's some ideal hydrodynamic terms. So this capital P is just my usual pressure. I have a convective contribution and then a shear viscous contribution. Okay, and unlike the first equation for the current, this latter equation should really be understood as an expansion in my parameter, in a small parameter, which is the ratio of my mean free path, little l, divided by capital L. So I can sort of schematically think of that like this. And this second term, or this final term, also hopefully reminds us that even for this shear viscous term, okay, this is sort of it's intended, at least formally, to be a small correction to these leading order terms. The leading order terms describe the behavior of my fluid in thermodynamic equilibrium, and this shear viscous correction describes the relaxation to thermal equilibrium. This is a dissipative coefficient, right? And very schematically, you can think that this is proportional to your thermodynamic coefficient times the mean free time. Okay. So for all the kinds of fluids that we'll think about today, this is sort of a reasonable guess for shear viscosity. Okay, and you can calculate it microscopically, and it turns out to be pretty accurate. Okay. So let me emphasize at this point that nothing in this story relies on microscopic classical versus quantum dynamics. Okay. At least occasionally when I talk about viscous electrons, people get confused because they think degrees of freedom in metal somehow feel intrinsically quantum mechanical. But everything I've said here is classical. And I think that you should understand why, even though the microscopic degrees of freedom may be quantum, the hydrodynamic equations are the boring classical ones that we know and love. The reason for this is the same reason that if you open up a thermodynamics book, you don't need to talk about classical thermodynamics and then quantum thermodynamics. Okay. Principles like the first and second law hold regardless of the microscopic dynamics. Okay. So it's the same principle at work here. And when we talk about viscous hydrodynamics and electrons, we have in mind a sort of classical description of the dynamics. Okay. The only place that quantum mechanics will enter into this story is in all of these coefficients. So shear viscosity, pressure, these depend on microscopic details and do indeed have sort of funny signatures that are special to electron liquids and metals, but that's it. Okay. Everything else is sort of standard. Okay. So now let's turn back to this question of electron liquids and solids. So, this discussion really would have held for any liquid, at least any liquid with Galilean invariants. What's special about solid state systems? So I thought that sort of a fun way to see why solids are a little bit subtle, why you can't just apply these equations too naively, would be to just try and apply them and see that we make a sort of stupid physical prediction. Okay. So let's try to make a physical prediction about the behavior of solids, assuming that solids obeyed Navier-Stokes equations, coming from plugging this constitutive relation into my equations of motion. Okay. Now, before we make a prediction, we need to think about what a solid state physicist could actually measure experimentally, right? If we're going to talk about dynamics of electrons or phonons in solids, this isn't visible with the naked eye. Okay, so we need some kind of clever experiment to detect this physics. And the sort of textbook experiment that you would do in solid state would be, to take a chunk of your metal, to hook some current leads into the metal. Maybe you put this one at some voltage V0, ground this one, and then to ask how much current flows through the device. Okay, so we just measure the current I0 flowing across this device, and essentially measuring this number R, the resistance of my block of metal, tells me about dynamics of the underlying electrons. And as sort of lame as this experiment might seem, this is really one of the standard ways that solid state physicists use even today to try and back out information about dynamics. Okay. All right. Now, very quickly, I just want to put this textbook equation in a form that's a little more practical. So this equation is awkward because all of these quantities are sort of global, right? They depend on the sample shape, but it would be more useful to have a local equation. So if this block has length L and cross-sectional area A, right, I can just write this equation in terms of the local electric field, the local current density, which is I0 divided by A. And if I then define the resistance R to be L divided by a number sigma times A, then these three equations imply that the current density J will be sigma times the electric field. And all of these quantities are local, like they make sense sort of pointwise in the solid. And so our goal will be, for now, to use hydrodynamics to try and calculate this quantity sigma. Okay. And let's ask whether, viscous fluid dynamics has any interesting implications for the form of conductivity sigma. Okay. So the first thing to remark upon is that when we write V equals IR, this is really a sort of linear response relation. Okay, so we have in mind that we started with a solid where, at least in aggregate, nothing is moving. Okay, there's no net current flow anywhere. And then we added a sort of perturbatively small current on top of that background. Okay, so since I is perturbatively small, okay, we can just linearize our Navier-Stokes, our hydrodynamic equations, just to keep things a little simpler. Okay. All right. So now let's say we have our block here, right? We're applying a uniform electric field across the device. And just to put some coordinate axes here, focusing on 2 dimensions. So we might expect that this electric field is going to excite fluid flow in the x direction. So let me write down the x component of my Navier-Stokes or momentum conservation equation. So this will look as follows. Here, right, I'm just going to define the momentum density as mass times number density times fluid velocity. Okay. All right. So I have here the left-hand side of my Navier-Stokes equation. Let me just focus on these terms. And then on the right-hand side, because the electron fluid is charged, when I apply an electric field, there will be Lorentz forces acting on these mobile electrons. Okay. So on the right-hand side, there's a net force density proportional to the electric field. Okay. All right. Now at this point, this is a linear equation. Let's try to solve it with some simplifying assumptions. So, okay, first let's assume that the system is homogeneous in the x direction, or at least approximately Yeah, let's assume the system is homogeneous in the x direction. So we'll just cross out this term. Then we'll say that our fluid velocity and electric field are proportional to some plane wave solution. Okay. This is sort of, just saying if we modulated the electric field with some wave number k and angular frequency omega, what would happen? Okay. So you plug this into this equation and use the fact that the local current density of electrons can be approximately written as minus electron charge times rho times Vx. And after a couple lines of algebra, you find that your conductivity is equal to density E squared over m times 1 over nu k minus I omega, where this parameter nu is my kinematic viscosity eta over m times rho. Yes, yes. So just remind. Okay. All right. So this is so far so good, hopefully. Except there's an important physical problem, which is that if we go back to our sort of experiment, which we could imagine doing on the tabletop, you may have done this in freshman physics. You may realize that, well, when you write down V equals IR in freshman physics, you don't have in mind some finite frequency or finite wave number effect. You just have in mind a static setup. Okay, there's a static electric field in the system. You generate a finite current. Okay, so the desired limit of these equations is to send k and omega both to 0. And in this case, we see that our conductivity diverges. Okay. So why does the conductivity diverge? Well, actually, if we go back and look at this equation, it sort of makes sense, perhaps, that if you look at a static setup, then this term can't be included because that depends on a time derivative. And if we're looking for something strictly homogeneous, this term also can't show up. And so there's really nothing left other than the Lorentz force. Okay. So this equation has no solution. It's 0 equals not 0. And this means that, in all of the metals that we see in the lab, that we work with in our everyday life, okay, momentum is not a good conserved quantity. All right. So this is sort of a long-winded way to answer the question of why viscous electron hydrodynamics is not a very old subject. Okay, but hopefully here you can now see quite explicitly what's going on. Okay. All right. Now, right. So if we want to make actual predictions for metals, the first thing we would need to do, right, is to correct this sort of awkward infinity in our theory. So the way that we can correct for that, at least schematically, will be to take our Navier-Stokes equation from before and just put in by hand an extra term, sort of like a friction term that can relax the momentum. Okay. So there's an extra parameter, I'll call it tau sub mr for momentum relaxing timescale. Okay. And this term basically says that if you have some momentum density in the system, it will exponentially decay with this timescale. Okay. And now if we repeat our calculation, now we find a more reasonable looking formula. which looks like this. Okay. So we've just basically added a fudge factor in the denominator here, which makes it finite, even if we take this k and omega to zero limit. But the problem is that, right, this sort of DC conductivity, this textbook calculation that we would have wanted to do and ideally relate to hydrodynamics, turns out to be independent of the sort of beloved shear viscosity. Okay. And this bulk conductivity entirely depended on this kind of undesirable fudge parameter that we needed to put in just to make this all work out. Okay. And there's an important physical lesson here just to reiterate, which is that because momentum is not conserved in a metal, anytime you have a sort of net finite density of electrons, if you want to have a finite conductivity, you must find a way to somehow relax the momentum that's dumped into those electrons by the Lorentz force. Okay.
For a finite channel, you could put no boundary conditions or something to get it.
Yeah, so I'll come back to that a bit later. Yeah. Okay. Okay. Yeah.
Navier-Stokes Equation approach, do you consider the no-state boundary conditions?
Yeah, so at the moment, I haven't talked about boundary conditions and geometries yet. I'll come to that a little later. Yeah, there's a few other sort of elementary considerations I want to clear up first. But yeah, we'll get there soonish. Okay, good. Okay, one other quick point. So, you know, one can do microscopic calculations, right, for what is this parameter nu, and you find that for electrons, this is proportional to their sort of typical velocity, which is Fermi velocity, multiplied by a scattering time, let's say, for electrons. And then there's a factor of 4 in 2 dimensions. That's not so important. Okay. All right, so let me now return to this question that I was vague about at the very beginning of this talk, which is whether electrons are described by hydrodynamics in general. So if by hydrodynamics, you mean that electrons are governed by the Navier-Stokes equation or something sort of approximately the Navier-Stokes equation, then we'll see that the answer is almost never, but sometimes just barely. Okay. It's very hard to enter a regime where electrons can be described by your textbook Navier-Stokes equations, although it's just becoming possible in experiments. However, I would argue that one should think of hydrodynamics as not just the Navier-Stokes equations, but instead as the theory that describes thermalization on late timescales. And in that case, there is a hydrodynamic limit for our boring metal. Okay, even if this parameter is pretty big, we can still find a sort of hydrodynamics for an ordinary metal that describes its ultra late time behavior. Okay, and those equations will correspond to an equation for charge. We won't write one for momentum because we know momentum is not a conserved quantity. And the thing we can write down is Fick's law. Okay. Okay. So I would advocate for thinking of this as the hydrodynamic limit that would describe an electronic system, a typical one. All right. This diffusion constant D, by the way, is when multiplied by some thermodynamic prefactor is equal to the DC conductivity, which in our model from before was given by this formula. And in solid state physics, this is known as the Drudo formula. Okay. All right. Any questions before I continue? Yeah.
Basically saying that the hydrodynamics
So, okay, so if you take copper, for example, at room temperature, then the theory that describes thermalization in copper are diffusion equations. Actually, it can be a bit more nasty if you remember that electrons interact with a very long-range Coulomb interaction, but sweep that under the rug, and you would have two diffusion equations, one for energy and one for charge. If you want to see sort of viscous flow, that is not just, copper does not have viscous electron flow. And for that, we'll need to talk a little more carefully and, you know, what materials may be sort of so clean and effectively have this tau MR that's so big that you can see viscous hydrodynamics kick in. So that's the next thing I'll discuss. Yeah. All right, let's move on to that then. Okay. So as I've belabored, I hope, so viscous hydrodynamics means that we need, let's say, what I'll write as LEE, but this is intended to be a sort of momentum conserving mean free path for electron collisions, right? We need this to be much smaller than the corresponding length scale for momentum relaxing collisions. This you can just think of as the sort of typical velocity in the problem, which is Fermi velocity multiplied by a momentum relaxing timescale, the same one we introduced before. Okay. Right. So let me now give just sort of a quick kind of, but let me sidetrack for a little bit just to talk about experimental systems, just to give you some numbers to have in mind, just to appreciate why it turns out this is a very hard regime to access. Okay. So I'll focus on the example of graphene. So graphene is a two-dimensional honeycomb lattice of carbon atoms. I'll focus just on a single layer. Okay. You don't need to know what its microscopics is. Just keep in mind it's two-dimensional. Okay. And back in the early 2000s, graphene was sort of isolated and studied experimentally using essentially pencil lead and Scotch tape. Very beautiful little story. And the way that they did this, okay, which at the time seemed like it made pretty good devices, was that they would, you know, isolate a single layer of graphene. But, you know, this is one atomic layer thick. If you try to hold it in your hand, it will break apart. Okay? So you have to put it on something to stabilize it. And what they would put it on, just to sort of, you know, cut the story short, is essentially glass, okay, silicon dioxide. And okay, you know, both of these materials are sort of maybe moderately pure, but there are some impurities, particularly actually in this glass substrate, okay? And for all of these impurities, you know, these are typically charged impurities, and there are so-called charge puddles that form in the graphene layer. This will form the dominant source of disorder and momentum relaxation, okay? And it turns out that the momentum relaxing length scale that effectively arises due to these impurities, this is a complicated function of electron density, temperature, et cetera, but just to give you a sort of typical ballpark number, this would be about 100 nanometers, okay? And, you know, this might seem kind of small, but on the other hand, you know, this is maybe pushing, I forget the exact numbers, but it's around 500 unit cells in the lattice, okay? So when you think about it this way, right, these were pretty clean devices. Maybe every 100,000 atoms or so. It's as if you have a defect every 100,000 atoms. It's quite small, okay? But it turns out that this is really not good enough if you have a material that's this dirty, you're not going to see this hydrodynamic, or this viscous regime where this condition holds. So for this same device, I won't justify these calculations, but for this same device, you find that this scale would be let's see. Sorry. So TF here is the Fermi temperature, which in these devices is thousands of Kelvin. And plugging in numbers here, it turns out you get, again, these are just order of magnitude estimates. You get something like this. So at about 100 Kelvin or so in temperature, you might see a mean free path for momentum conserving collisions, which is about 500 nanometers. Okay. And this is an unfortunate property of metals. So most metals are described by Fermi liquid theory, and Fermi liquid theory tells you that even if microscopically the interactions in metals are pretty strong, the sort of effective quasi-particles that arise, that are addressed by interactions, end up interacting weakly. Okay. All right. Now, you can't get to too high temperature. You might say, well, fine, at room temperature, this number is smaller than this one. The main reason you can't do that is because typically by room temperature, maybe even by 200 Kelvin or so, there's another kind of momentum relaxing process called Umklapp, which makes this momentum relaxing scale effectively go to zero for our purposes. Okay. And so there's kind of this sweet spot that you would need to be at a high enough temperature where LEE is small compared to LMR, but you'll also need a sample where LMR is better. Okay. This one is not good enough. Okay. So in 2010, people found out how to do this, and they basically just sandwich another material and make these heterostructures. Okay, probably no one here cares about the other material, so I won't say anything about it. But these materials are sort of atomically well aligned. It turns out that this is a very clean interface, and you can improve your momentum relaxing mean free path by at least an order of magnitude. Okay. So now we're in business, right? If we compare these two length scales, indeed, it's sort of reasonable that at around 100 Kelvin, this one might be, quite a bit smaller than this one. So we might think we have a chance to really see viscous Navier-Stokes equations arise in this device. Okay. Yeah. That's a good question. So how do you measure LMR? So the way we do this usually is just by measuring this DC conductivity, right, which is rho E squared over M, and then this would be LMR divided by VF. These are all thermodynamic parameters, so you kind of know what these are going to be, and what we're left with is LMR. Okay. All right. Okay. Now, okay, this was maybe a long-winded way to emphasize to you that most metals, okay, do not have LMR much larger than LEE. It's usually more like the opposite limit, okay? But there are a few other metals that have very long momentum relaxing mean free paths, all of which are arguably more interesting than graphene for reasons I'll talk about at the end, at least to me. So just to give you a brief laundry list of some other materials. Okay, so gallium arsenide is also a pretty simple system, which is a semiconductor. More exotic and interesting would be some of these other things with complicated chemical formulas. I'm not sure what all of them are called. This one is palladium cobaltate, I forget. what these are called. Okay. Yeah. And typically what experimentalists do in these cases is they just say, oh, my mean free path LMR is microns. And so therefore, maybe we can have a sort of similar regime as in graphene. Okay. All right. So now let's discuss how would we, if we have this material graphene, which we think might give rise to viscous electron flow, how would you actually see it in the lab? Remember, we can't take pictures of the electrons, at least not until the last 2 years or so in this setting. So at least back in 2015, we needed to do somewhat more mundane things. To get a sense of what we might be looking for, let's begin by sort of estimating the Reynolds numbers that we might expect for these flows. Okay. So the Reynolds number, we might estimate as our typical fluid velocity in whatever flow we're hoping to see, multiplied by maybe the length of the device, capital L. So this is device size. And then divide by kinematic viscosity nu. And if I combined a bunch of formulas that I've written down before, I'll get L over V Fermi, LEE. There's before somewhere, I'm not going to worry about it. And the typical velocity, flow velocities that you can access are going to be fractions of the Fermi velocity, but probably not larger than the Fermi velocity. So let's just wing it and say about 1/10 of the Fermi velocity. This is about VF is 10 to the 6 meters per second in graphene. So these are actually quite fast. Okay, just moderately slow compared to the relevant velocity scale. Okay, now this sort of sucks because the VFs cancel. We have length of our device over 10 LEE. Typically, the device sizes that you're looking at in experiment, the sort of size of this graphene layer that you can grow will be maybe 10 microns. Any more than that, and it starts to get crummy. It's very disordered. These very pristine samples, are usually not much bigger than 10 microns. And well, this means we have a Reynolds number of around 2. So this is not going to be a highly turbulent nonlinear flow. Okay, we're very, very much in a creep flow limit of Navier-Stokes. Okay, and people have tried very, very hard to reach a turbulent regime, and I don't think they've been successful. Okay. All right. Yeah. I would say in practice, no. One reason is that the induced magnetic fields, there are factors of C in Maxwell's equations, and C is a big number. So these induced fields tend to be very small. And so for most purposes in these experiments, you can think E is purely potential. Yes. Yeah. So MHD in sort of astrophysical plasmas is quite a different limit to that regime is not reached in these electronic systems. So people have actually, I will talk about if you apply magnetic fields, there's sort of cute things that you can look for, but not in that regime. For us, the magnetic field is sort of a static, uniform thing. We can turn it on or off, but it doesn't feed into the dynamics. There are a lot of papers that say MHD, and it's sort of inappropriate for this reason. Okay. So there's no graphene MHD, at least not as of today. Okay. Sure. So if you, in graphene, no. So also, the temperatures that we're interested in, right? These are like high TC scale temperatures. And this is not, No.
Okay. And if you have graphene, you can put it into quantum Hall states, right?
Yes, I'm not an expert on quantum Hall and graphene, so I don't want to reveal too much of my ignorance on that application.
Yeah, that would answer my question.
Okay. All right. Okay. So finally, let's start talking about how we're actually going to see this. Viscous, hydro, and graphene. So, okay, we're looking for creep flow in the Navier-Stokes equations. So this really means we're not going to worry too much about convective terms. We can write down linear Navier-Stokes equations. Okay, and we can also assume that our flows are incompressible. Okay, again, the speed of sound is sort of comparable to VF, pretty big. And so these will be incompressible flows. And in 2 dimensions, because graphene, right, it's a 2-dimensional material, there's a very nice way that you can solve these Navier-Stokes equations. So writing this sort of antisymmetric Levi-Civita tensor epsilon ij, you write the velocity as essentially the curl of the stream function, which is a scalar psi. You plug this into Navier-Stokes. So we take the curl of this equation. And remember, we have to keep in this sort of sad momentum relaxing term because it's not too small. Okay, it's kind of small, but not all that small. So we've got to keep it around. And we take the curl of this equation, right? This piece drops out. And we get that the Laplacian squared of psi is the Laplacian squared of psi times a number. I'll call this 1 over lambda squared. This length scale lambda is often called the Gurji length, and it's given by this kinematic viscosity times tau mr. And this turns out to be half of the geometric mean of our 2 length scales, one for momentum conserving, the other for momentum relaxing interactions. Okay, now this is really sad, right? Because if we plug back our numbers, just as a brief aside, we're going to estimate, well, lambda is like 1/2 of the square root of 4 times 0.5 microns, which is a small number. Okay, this is actually not too much larger than our LEE. But okay, we'll wing it. We'll say it's bigger than LEE, so it's good enough. And let's just see what we would see. Yeah. Okay. The reality, right, is that we're not seeing sort of deeply viscous flows. Okay, everything that we're seeing in graphene is sort of right on the cusp of being viscous. Okay. But okay, we're on the cusp of this, so let's be optimistic and see what we could find. So if we look at this equation, right, the first thing that we notice is that we want to look at flow on a scale, let's say capital L, that's small compared to this scale lambda. If the flows are big compared to the scale lambda, right, then this piece of the equation dominates. And that turns out to just generate ohmic flow. So the flows are really textbook, okay? The current is the gradient of a potential, that's it. So we really need to look at scales that are small compared to lambda so that this term, which came from viscosity in our Navier-Stokes equation, gets to win, okay? And then we could see viscous effects. All right. So experimental strategies. The simplest thing we might try is what is called Poisson flow. Probably said that badly. In the solid state problem, this is called Gurji flow after the Soviet physicist who realized that this effect might happen in the 1960s. Took 50 years to find it, but okay. Yeah. Oh, sorry. So VF is Fermi velocity. So it's sort of the typical velocity scale of the electrons in the problem. So if you look sort of microscopically in the system, you would see, electrons zipping around at this velocity in all directions.
And the sound speed is comparable?
Yeah. So the sound speed, Vs for sound, turns out to be Vf divided by square root 2.
Why would that justify?
Well, because 1 over square root 2 is big compared to 1 over 10. So again, we're trying to be generous here because it's a hard problem. I mean, there are slightly better justifications because if you look on long enough scales, essentially the decay time of transverse flows is much slower than the sound propagation time. So that's really the better answer. Yeah. Okay. So, all right. So let's now talk about maybe the simplest possible experiment that one could try to do to see this effect. It turns out to be imperfect, but okay, one thing you can try is to just carve a narrow channel into a metal and look at the resistance of this channel. Now, keep in mind, right, this really has to be a tiny device. This is nanometer, micron scale devices. You can't really get smaller than that, okay? But okay, people are capable of doing this these days. So we could carve a very narrow channel of width W into a metal. So by channel, I mean that the electrons can't flow here or here. Okay, they have to flow through the middle. And again, we apply an electric field here. Okay, so we can write down our Navier-Stokes equation, just focusing on the transverse flow, right? So we'll have some shear stresses, and this has to be balanced by the Lorentz forces and our momentum relaxing friction, okay? Now we come to this issue of what to do with this. To solve this equation, we need to impose boundary conditions. The simplest thing we might do, this is sort of the standard in conventional fluid mechanics, is to impose no slip boundary conditions where Vx is 0 at the boundaries, okay? And if you do that, you can solve this linear equation exactly. You find Vx is some constant times 1 minus some hyperbolic cosine factor. This function C, C is just minus E tau mr over m times Ex, okay? All right. Now, remember that, okay, until very recently, we were not actually able to image the velocity flow directly. So that's not what you would measure. What people tried to measure instead is the resistance of this device per unit length, okay? So if I look at the resistance in this channel, divide by L, this is equal to the electric field in this device divided by the total current flowing in this device. The total current flowing in this device is just minus E times rho. This is the charge density. And then I just integrate the current over the device. This is a calculation you can do, and you get 1 over your DC conductivity times some other hyperbolic trig function, complicated thing in the denominator, okay? All right, this sigma DC is the Drudo formula over there. All righty. So now let's analyze this formula a little bit. So, as you might expect, if the channel is too big, okay, then we just see that our resistance per unit length is basically 1 over the bulk conductivity divided by width. And this is a textbook formula. Here, width is the cross-sectional area because we're in 2D. So this is just our standard formula relating bulk conductance to global resistance. There's nothing we can see that's special, okay? So we have to be in this regime where the width is very small compared to lambda. In the regime, we solve these equations and we see that R over L is approximately 12 times shear viscosity over charge density squared times width cubed. Okay, this is nice because this has some sort of key predictions that one can look for in experiments. Okay. So the first one is that there's a different power of W in this formula and this one, right? And it's a pretty different power. So you'd hope that you can easily tell them apart. Okay, actually it's a little harder than it sounds, but people have tried and there do seem to be materials that are kind of compatible with this 1 over width cubed. The other thing is the temperature dependence in this shear viscosity is quite unusual. So the shear viscosity is proportional to our momentum conserving mean free path. And on the right board, I told you that this is roughly 1 over temperature squared. And this is a very unusual temperature dependence. Typically, when you have a good metallic conductor, the resistances would rise with temperature. Some even take that as the definition of a metal. But this is a system where you heat it up and the resistance would go down. So it's a very striking effect in a good conductor. Okay. Now, sadly, there's a problem with this experiment. I don't think this is actually a very good way to look for hydrodynamic flow. And the problem with this experiment is that there are other boundary conditions that give very different physics. Okay. Yeah.
Can you give an intuitive picture why the reductions would go down with like hydrogen?
So, okay, very quickly, this has to do with some microscopic solid state physics associated with Pauli exclusion principle and collisions. So when you have a Fermi gas, right, so all the sort of low energy excitations live at a finite momentum, so the outside of the Fermi sphere. And at finite temperature, this gets smeared out to have a width T. And electrons basically can only scatter within that narrow shell. And so their scattering rate for a two-body collision is T squared. So then divide by that to get a mean free path, that's 1 over T squared. Okay. Yeah. Okay. So let's say the problem with this setup A, the Poisson flow, is that I can also pick for you another set of boundary conditions that give very different physics. This boundary condition set may even seem more microscopically reasonable, because suppose I had a channel and I etched it very clean, so that essentially if a particle hits the boundary, it just scatters off, at the same angle of incidence. So then I would get no stress boundary conditions, which in fluid mechanics will just be the derivative of my velocity being 0 at the boundary. What does this do? Okay, well, it turns out you can just eyeball that the solution is that the velocity is uniform and it doesn't depend on viscosity at all. Correspondingly, my resistance per unit length is always given by my sort of textbook Drudo-like bulk picture. There's no length scale corrections that are that can tell me about viscous effects. Okay. So for this reason, these Gurji experiments are quite awkward because we don't actually know what the boundary conditions are. Life being what it is, there'll be some kind of intermediate between these two boundary conditions, and there's a fudge factor that's hard to determine. Okay. All right. So a better idea, there are two that are a little better. So one is to look at what is somewhat annoyingly called non-local transport. I really, really hate this terminology, I have to say, because actually this is local transport, okay? It's completely backwards. So suppose we, rather than looking at sort of flow down a channel, instead let's sort of take the channel and inject current on the sides like this. There are many versions of this setup, but this is the simplest one. Now, if you look, how will current flow in this device? It turns out, without going through the details, in a sort of ohmic, this is basically a width large compared to lambda regime. The current will sort of do this and, kind of tries to straight shoot across the channel. Nothing that interesting happens. If you look, however, in this opposite limit, you find that you sort of form this series of whirlpools, vorticity, et cetera. And this actually has a sort of nice experimental signature. So if you look at, let's say, the voltage drop between 2 points off to the side like this, you find that over here, where the voltage drop may have been positive, over here in the viscous regime, if you pick these points correctly, you can find this voltage drop flipped sign. So this is sort of a nicer prediction, right? Because it's qualitative. Even if you're not sure about orders of magnitude or boundary conditions, et cetera, it's pretty hard to, impossible to get this effect in that limit. Okay. So this is a better signature. It at least rules out for you that you have sort of ohmic conventional transport. Okay. Now, okay, there's still one subtlety with this. I don't want to get too deep into the weeds, but turns out that for this experiment, you have a very hard time telling apart this picture from another sort of also not viscous picture where essentially there are no interactions at all. If you have no interactions at all, it turns out this also can give you the same negative voltage drop in this device. So it's very hard to tell apart what's called ballistic transport versus viscous flow. Okay. So with this said, my favorite experiment.
With ballistic, it'll just bounce, rattle back and forth as it goes down the channel, or what?
It's a little more subtle. So in the ballistic regime, basically, what you worry about is there are rare collisions that can sort of knock an electron into these probes. And it turns out when you do the calculation that the sign ends up being the same as it is in this case. I don't remember the sort of details more than that. But so basically there's an LEE out in front of delta V in the ballistic regime.
Okay, but it's that left pattern, but occasional scattering in the wrong direction.
It's a little tricky. I wouldn't, it doesn't look like the ohmic flow pattern. It looks somewhat in between these two limits in some sense. But the sign change matches this one, which is the important thing. Okay. So my favorite experiment of all is essentially flow through narrow constrictions. So this one is, qualitatively similar in spirit to the channel, except that the channel is very short. This is useful because the most important boundary condition in this problem is that the current starts off flowing like this. It sees a wall. It can't go through the wall. So all the current gets squished through the constriction. And this turns out to give sort of different predictions in all the regimes that we've worried about. So if you have ohmic transport, the conductance, which is basically 1 over the resistance of this device, is basically independent of width. Strictly, there's a logarithm, but no one cares. Okay. If you have ballistic transport, this is proportional to width. And if you have viscous transport, it's proportional to the width squared over the viscosity, which is proportional to LEE. And this, again, gives you a very peculiar temperature and width dependence that you can see the onset of in experiments. Okay. In particular, this value is smaller than this one, which is a very striking prediction that's been seen. Okay. Yes. Yeah. Okay. All right. So I would say up until now, I've been telling you about how we've really tried to use ultra pure samples of graphene to see viscous flows of electrons. This is cool. Okay, you can get magazine papers out of it. It's a fun thing to do, but what comes next? Okay, this effect is by now pretty well established. So for the rest of the talk, I'd like to sort of mention a couple of perspectives that I have on sort of what both solid state physicists can learn from this adventure and perhaps what sort of exotic hydrodynamics can be seen in solids perhaps more easily than in other contexts. Okay, so first let me mention briefly about what solid state physicists might learn in the long run. An important lesson, I think, of this whole story is that formula I might have just erased. So let me rewrite it, which is we found earlier our wave number dependent conductivity, sigma of k and omega. Right. And we said that this in our toy model had the following form. If you set k equals 0, okay, in this formula, this gives you a sort of textbook result, which is kind of sad. Okay. It's actually a very hard thing to see experimentally. You will not see sort of beautiful so-called Drudo peaks in all that many materials, but occasionally you do find them. Okay. And it's an old prediction, so it's hard to get excited about. Okay. Now, if instead you happen to take the other limit, so if we look at k not equals 0, right, now this is a more exciting formula because we haven't dropped the shear viscosity, and the shear viscosity is proportional to another scattering length, right? Not, or scattering time if you prefer, not this tau mr, but it's another time scale tau ee. So if you could measure the k dependence in this object, you would learn about dynamical processes that are invisible in bulk resistivity. So this is, I think, a sort of long-term lesson for solid state physics that's very valuable, that looking at the spatially resolved transport can often both be better than looking at finite frequency transport and can also give you a sort of wealth of information about microscopic dynamics, which was invisible in conventional probes. Okay. Just as one quick application of this idea, it turns out that, so this is some of our recent work. If you take superconducting thin films just above TC, from above, it turns out that you see a sort of very similar looking formula to this one. Okay, and this this sort of momentum relaxing scale, in this case, it's not momentum, but something else, which becomes very long-lived, close to TC. Okay, right at TC, right, the bulk conductance diverges. This is sort of the simplest manifestation of superconductivity. And what's left turns out to not be singular. If you look at finite wave number, there's a finite conductivity. Okay. Sorry, what? Possibly. I think the physics here is, so this is effectively a classical effect related to vortex dynamics. Sure. Yeah. Yeah. Anyway, this is largely actually pretty old physics that we've just resurrected, to make this analogy. But nevertheless, I think this is sort of a very experimentally accessible kind of prediction. Okay. Maybe something more interesting for this audience would be, so are there kind of cool hydrodynamic effects that are surprisingly easily accessible in this electronic setting, but maybe hard elsewhere? Okay, So, good. So recall that, so when we derive these Navier-Stokes equations in a textbook, okay, an important assumption that goes into that derivation was Galilean invariants, okay? So essentially the ability to look in all reference frames and see the same physics. In this electronic setting, it's actually kind of unnatural to expect this symmetry to arise, right? We have an ionic lattice. The ionic lattice is at rest in one frame and not in other frames. So definitely we should not really have boost symmetry. It turns out in graphene, for various microscopic reasons, this is a good approximate symmetry because the Fermi surface is a circle. It's a very good approximation. Okay, but you know, there are other materials that are anisotropic. And so we might expect that in general, we will not have this symmetry. And so the constraints that we found on the stress tensor and the charge current will have to be relaxed, okay? And there will be more terms that we can write down and look for. Before we talk about anisotropy though, let me describe a sort of very simpler rather, sort of phenomenon that you can look for, which is just breaking essentially parity and time reversal with a magnetic field. I should say maybe. Okay, combination is conserved or is preserved. So this is a PT symmetric theory, but you have neither P nor T individually. Okay. So what does that do? So it turns out that this gives you another allowed coefficient in the stress tensor. So if we write down our stress tensor, so in 2 dimensions, okay, we're going to focus on 2 dimensions for the rest of the talk. Kind of already have been, but yeah, in 2 dimensions. So you can write down the sort of old stress tensor. Let me not rewrite that whole thing down. But because you've broken this combination of symmetries, it turns out there's another coefficient that you're allowed to write down, which looks like this. Okay. So this coefficient is called Hall viscosity. So what does it correspond to? Yeah. Okay, let me do this. Yeah. Okay. So this Hall viscosity is kind of a funny term. If you apply sort of one component of shear stress to it, the object will try to sort of deform the other way. So you get kind of funny phenomenology. And there are some cool papers discussing that. If I write down the Navier-Stokes equations directly, we find that Hall viscosity has a particular contribution. So in our Navier-Stokes equation, okay, we get these are the usual terms within linear response. And then this Hall viscous term does the following. I might have a sign backwards, but in a nutshell, it's this. Okay. So it essentially says that you get a correction to the flow pattern, which is kind of 90 degrees rotated relative to the stresses coming from shear viscosity. Okay. All right. Now, in the electronic setting, when we apply a magnetic field, it turns out that, right, we don't really get zero here. We have both momentum relaxation, and also because we've applied a magnetic field to a charged fluid, we also have another contribution. So this piece is called the cyclotron or omega c rather is the cyclotron frequency equal to EB over m. This just tells us that, again, there's a Lorentz force acting on a charged fluid in a static magnetic field. Okay. So there's now two ways that we've broken momentum conservation in the system. But again, with all the usual sort of bells and whistles, if these terms happen to be small, we can try to look for the correction due to eta h in experiment. Actually, as far as I know, this Hall viscosity hasn't really been nicely seen in a lot of fluid contexts. And actually, I know of two cases where I think it's been found, one in graphene, just in a background magnetic field, and one in a sort of funny active fluid, which was engineered to have this effect. But in graphene, how this was observed is basically to take this same non-local transport setup and you look at the same voltage probe that I've erased by now, but turn on a magnetic field, and turn the magnetic field on, then basically flip its direction. And the asymmetry that you find in your signal is proportional to eta h, at least in the limit where these terms can be neglected.
You need a strong del squared, right? You have epsilon ij vj on both.
Right. So it's the same caveat that these terms need to be larger than these terms. So you have to crank the numbers microscopically. And again, it's kind of just barely working. But, okay. And just to sort of quickly remark here, eta h is basically proportional to eta times this combination. So it's a pretty small effect. But okay. That's Hall viscosity. So maybe probably the last thing I'll talk about. So Hall viscosity is sort of popular, but I think less popular, albeit still interesting, are the other anisotropic effects that can arise in metals. So if you ask sort of what does the kinetic energy of electrons look like in a typical metal? Well, the kinetic energy of electrons in a typical metal is essentially captured by typically a pretty complicated function. If you think about the Fermi surface of the metal, right, this is just the contour of the kinetic energy at the Fermi energy. So even in a pretty simple metal, like this one I mentioned earlier, palladium cobaltate, which was believed to have hydrodynamic phenomena, if you look at its Fermi surface, it looks more like this. So it's much closer to a sort of polygon than to a circle. Okay. So what do I mean when I sketch this curve? I mean that this, the kinetic energy, the single particle kinetic energy, epsilon of p, has hexagonal symmetry. So, okay, it might be something like p squared plus, I forget these functions, something like py cubed minus something like this, okay? So you might ask, if your microscopics has this kind of kinetic energy rather than this kinetic energy. So this one is Galilean invariant, right? This one is not. So we might ask, how important is this? Does it modify hydrodynamics in any interesting ways? So there are a couple of new phenomena that you can find when you break this Galilean symmetry. So all of them turn out to be dissipative corrections. So recall that the way we think about organizing hydro is via our constitutive relations. I'll write down the one for momentum explicitly because index placement is going to be important in 60 seconds. Okay. For the charge current, we find, so this term we had before, but now we pick up a new term. Okay. This is what Sean Hartnell has dubbed the incoherent diffusion constant. This effect arises from the fact that, with this hexagonal Fermi surface, the momentum and the charge current are now distinct objects, okay? And it's possible to have current flow without any momentum density, okay? So microscopically, you can think about this as follows. If you have a kinetic theory, for example, this momentum density will be the integral over momenta of your distribution function multiplied by momentum, whereas the current is this same integral multiplied by a different object, which is the gradient of the kinetic energy. Okay. When the kinetic energy is p squared over 2m, these things are proportional, but otherwise they're not. So whenever pi and j are not proportional, you'll always inevitably get this term. Sometimes this coefficient is small, as it is in graphene, but it is there. Okay. Turns out, though, that when you have an anisotropic Fermi surface, this term becomes very large. All right. What about the stress tensor? So in the stress tensor, within linear response, so we again just have this viscous tensor, but now there are new coefficients that we can write down here. So this eta JIKL. Okay, so first we have the usual shear viscosity, which can be helpful to write in this way. Then we have bulk viscosity. Bulk viscosity is usually extremely small in conventional liquids and gases. But for certain kinds of metals, this effect would not be small. It would be comparable to eta. It's just harder to detect because most flows we look at are incompressible, and so this piece vanishes. Okay, there's one more term that we can write down. Oops, sorry, like this. So this piece is rotational viscosity. And what this term does is it says that if you create a vortex in the fluid, even if it's sort of a global vortex, so the fluid is just rotating as if you changed reference frame, that is still not liked by this fluid. That will produce entropy, and the fluid will try to relax it away. Okay. Why is this effect allowed? Actually, maybe a better question to ask is why this is forbidden in conventional hydrodynamics. So all of the terms I've written down here are formally invariant under the orthogonal group in 2 dimensions. Okay, so this eta transforms it basically is invariant. Okay. So the way to see why this is forbidden in an ordinary fluid is to note that if you want angular momentum conservation in an ordinary fluid, so this, okay, so this would correspond to the following constraint. And after a couple lines of algebra, this tells you that you want your stress tensor to be symmetric. And it's this constraint that forbids rotational viscous flow in classical liquids, like air. However, in this electronic setting, there's no reason for this rotational viscosity to vanish. And in fact, you can do quantum kinetic calculations and you find this term is not zero. Okay. In a nutshell, the reason this term is generic is that if you imagine trying to rotate your fluid, you might think this is kind of like taking the Fermi surface of your electron liquid and rotating it. And I won't be able to draw this, but you get the idea. Okay. The lattice, however, has a particular orientation and it prefers the Fermi surface to be oriented relative to it in the right way. So it doesn't like the rotated Fermi surface in this. This is the origin of this term. Okay. Yes. Yeah. Now, all of these terms are compatible with continuous rotational symmetry. You would have to go to a higher order in the derivative expansion to see an explicit hexagonal symmetry term. Okay, yeah, most of that, so it's going to be invisible now. But okay, very quickly, so this rotational viscosity, what does it do in the equations of motion? Well, that's kind of sad. It turns out that if you add rotational viscosity, it does this. So again, this effect is basically invisible. But we have proposed one experiment for how to detect this using a sort of very symmetric device. And if you essentially prepare a device where you know that vorticity, sort of only vorticity, but no shear stress exists at a certain point, then if that point has local heating, you know that there's rotational viscosity. If not, then there's no dissipation due to a sort of global vortex means no rotational viscosity. Okay. In the last couple of minutes, let me mention one other cute thing and then I'll stop. So, okay, if we take the hexagon and we replace the hexagon with a triangle, just to sort of lower the symmetry a little further, there are a couple cute things that can happen here. So with a triangle, okay, it turns out that there's an invariant tensor under the symmetry group of a triangle that has a small enough number of indices that it might be nice to play with. So there's a 3-index invariant tensor. Maybe some of you are familiar with this from piezoelectricity. Okay. And you might think, okay, there's two things that I could do to hydrodynamics if you have this triangular symmetry. One is an ideal hydrodynamic effect, which is to add a stress which is proportional to velocity, but with this kind of funny triangular prefactor in front. And the other one is a dissipative correction. So here mu is basically density divided by a thermodynamic susceptibility. And correspondingly, when you write down that alpha term, you need to add it in the charge current. So this is what's called Onsager reciprocity. Okay, if you do microscopic calculations for electron liquids, you find that alpha is in general not zero. There's one constraint. This is positivity of a certain matrix of dissipative coefficients. But you find that K always equals 0. Okay. And what's curious about this K equals 0 is that actually, if you try to write down an entropy current, which is what Landau's textbook tells you should do, you find that this is compatible with an entropy current, but yet it doesn't exist. So I would say this is a puzzle that we're still in the process of sorting out. We think it has to do with emergent anomalies that arise in this fluid. But anyway, I figured I'd end on that note that, even starting with these very simple kind of classical hydrodynamic equations, we're sort of thinking of them in fun new ways, inspired by quantum electron liquids and other new phases of matter. And we're sort of still learning new things about fundamental hydrodynamics even today.
Sorry, I didn't get what is this lambda triangle lambda?
It's an invariant tensor under the triangular group. So if you apply 120-degree rotations or flip the direction of the x coordinate, you find that this third rank tensor is invariant. So no, well, it's physical. I mean, it's sort of like saying, if you have a material that, for example, is different in the x and the y direction, then you can write down new, like the elastic properties, if you stretch it in the x and the y directions, will be different. And that's possible because there's a fourth rank tensor which is invariant under this group, under the symmetry group. So it's sort of like, okay, so if we went to this equation, so basically all these three objects, the sigma x, sigma z sort of combo, double delta and double epsilon, these are all invariant under O2. So we could write all of them down, right? And generally we should, because they're all invariant under the symmetries of the problem. So it's when you have these very low dimensional point groups, it just turns out there are more kinds of tensors you can include. And this is the simplest group that has a third rank tensor, which sort of is more fun because it mixes, currents, and like velocity and density get mixed in ways that are not allowed in ordinary fluids.
What's the underlying lattice there? I'd be making hexagons out of those.
So yeah, you would probably start with a hexagonal lattice and try to explicitly break inversion. So basically, this theory will have it's invariant under inversion plus time reversal, but neither separately. So if you preserve this combination only on a hexagonal lattice, then you might expect to see this. Yeah. Mm-hmm. So people have tried. Some of these materials that I wrote down very briefly are three-dimensional crystals. I think it's just harder in 3 dimensions. I don't think we really understand why, but maybe one sort of heuristic reason why is that many of these 2D systems are sort of very clean because we're just growing sort of a single layer. They're substrated on very clean sort of thin films themselves. There's a sort of fairly low density of states. So yeah, but we don't really know why graphene gallium arsenide seem to work better. Yeah.
So for the all this property discussion, you commented on the magnetic field. Is it possible to get all the properties from the very curvature that you don't?
Yes. Yeah. There are a few papers on this actually. Even like free fermions, you can calculate all viscosity. So, I mean, there it's not as meaningful, arguably, but one can do the calculation. Well, you need, I mean, you need to break time reversal, but free fermion with the right band structure can, like, you have a sort of Berry monopole, you get all viscosity.
On that graph wall, you define a new spatial scale lambda. So what's the difference between that scale?
It's essentially the scale that governs the transition from viscous flow to ohmic diffusive flow. So, yeah.
Talk about the let's say I have a second Fermi surface and I have just one band, and how the Boltzmann sort of the distribution function, the Boltzmann equation look like, so that I can have
So Let's see, I haven't erased this. Okay, so you do this computation, right? And you find that pi and j are different microscopically. Okay, so now what you have to ask is, basically, you can formally think of sort of take the overlap of these vectors, right? And then subtract that out. So kind of project out the momentum out of the current. And then you can ask, does the density couple to that? Basically, if you take the streaming term in your Boltzmann equation and you multiply that by density, which is sort of integral of f, sorry, you have to put, so if you do something like this, basically, does this couple to j? And it turns out that it does, right? This is just VF, which is just sort of j by definition. But this is important because it means that the part of j which is orthogonal to momentum will relax in the collision integral. And if you sort of follow this standard Chapman-Enskog procedure, you find this coefficient. Sorry, why doesn't it come from momentum? It's just so, okay, very, very roughly, so abstractly, so momentum, think of some high dimensional vector space of like all the possible distributions in kinetic theory. Momentum is like one direction, okay? And current is here. So part of the current overlaps with the momentum, that gives you this. Okay, so this is kind of like the overlap of current with momentum times momentum. In fact, this overlap of current and momentum is properly understood as density. You can show that pretty generally, and velocity is sort of the prefactor in the distribution function multiplying pi. But then for what's left, there's just no reason that kind of doesn't couple to momentum. That just does its own thing. And that turns out to decay and give you this piece. So this is the piece that's sort of orthogonal to j. Maybe it's not actually too hard to see in kinetic theory, but I think I would need to sort of maybe go through a few more steps. But it's in papers that I think it's pretty transparent. Yeah. Yes. I mean, the effective mass tensor is diagonal for the hexagonal liquid. There's no, it has to be by symmetry. So this is a separate effect.
Again?